You generate and consume data every single day.
Oh, absolutely. Constantly.
Right, you take a photo on your phone, you send a text, stream a song, and if you're like most people, you probably just picture all of that data as this flat, endless string of ones and zeros.
Yeah, just sitting on a hard drive somewhere.
Exactly. It's incredibly linear. Most of us imagine data as like a tape measure just stretching out into the digital distance. But today in this deep dive, we are going to completely shatter that mental model.
We really are. It's a huge paradigm shift.
We're going to look at data not as flat strings, but as three-dimensional geometry. Like, we're going to treat files as topological knots.
Which is just a fundamental shift in how we process information entirely. We're looking into this highly technical, frankly mind-bending project called Bitwise.
Yeah, and our sources today are from this dense manifesto-like README file that it maps out an entire ecosystem of tools.
Right. It touches on everything. We're talking DNA sequencing, sub-100 bits per second voice codecs.
Edge-native blockchains.
Yeah, and even formal mathematical proofs about the energy limits of the universe. It's wild.
The scope is just massive, and our mission today is to decode these complex mathematical concepts and reveal the core premise tying it all together, which is, what if we've been storing and compressing data entirely wrong this whole time?
Just because we've ignored its actual shape.
Right. So to understand how Bitwise treats your everyday data, we have to look at the starting point for this whole stack, which is biology, specifically DNA.
Right, DNA, the original biological data storage system.
Exactly. Now, Bitwise starts off with what they call standard 1D packing. Let's break that down. DNA is made of 4 bases, right? A, C, G, and T.
And because there are only 4 options, you only need 2 digital bits to represent a single base, so like 0, 0, 1, 10, or 11.
Okay.
And since a standard byte of data holds 8 bits, you can fit exactly 4 DNA bases into a single byte.
Which gives you this immediate 4x compression ratio right out of the gate.
Exactly. And the documentation says the resulting speed is like one of those ultra-fast search functions programmers use, like grep, to scan millions of lines of code in milliseconds.
That speed is incredible. But like you said, that's just the 1D packing. That's the flat tape measure approach.
Right.
Where Bitwise breaks away from traditional computing is that it refuses to stop at a single dimension. It scales the architecture up into what they call the 54-dimension helix stack.
Yes.
Okay, wait, let's stop and unpack this. Because the phrase 54 dimensions sounds like, I don't know, quantum physics or sci-fi.
It does sound a bit sci-fi.
If we're just talking about computer files, what actually are these dimensions? We need to ground this a bit.
That's a really crucial distinction to make. When we say dimensions here, do not think of string theory or parallel universes.
Okay, good.
Think of a highly detailed address book. In an address book, a person's name is 1 dimension of data. Their phone number is dimension 2. Their zip code is dimension 3. Bitwise is doing that for biology. So think of the base DNA sequence as just layer 0. That's your flat file. But biology isn't just the sequence, it's the whole context around it.
Yeah.
So Bitwise stacks 54 parallel annotation layers directly on top of that flat sequence.
So we're talking about, what, epigenetic marks?
Epigenetics, histone modifications, cross-species conservation data, all the way up to the actual 3D physical folding of the RNA inside the cell.
Wow.
Yeah, they track 54 different traits for every single piece of DNA, and they treat them as independent, self-describing streams called flow frames.
But logically, I mean, if you take a base file and suddenly slap 53 more layers of data onto it, shouldn't the file size just absolutely explode?
You'd certainly expect it to. I mean, a standard human genome reference file is about 0.77 gigabytes.
Right.
If you multiply that by 54 full layers of data, you'd expect a massively unwieldy file. But the Bitwise 54-layer genome comes in at only 9.48 gigabytes.
It's only like a 12.4x expansion. And the reason it avoids blowing up is because of this concept the source is called dilation, or my personal favorite term from the docs, the squirrel cheek method.
It's a great visual.
It really is. It's essentially like packing a suitcase. The 1D packing is just laying your clothes flat in the main compartment.
Sure.
But dilation is realizing, hey, I can stuff my socks inside my shoes, and I can roll my phone chargers up inside those socks.
Right.
You're adding immense depth and utility without actually expanding the outer, rigid volume of the suitcase itself.
That analogy perfectly illustrates it. Bitwise realized that not all data layers are equally dense.
Okay.
The base sequence of DNA is incredibly dense. You have a critical data point at every single step. But regulatory data, like transcription factor binding, is very sparse.
So it's mostly empty space.
Exactly. It might only have a meaningful piece of data every 200 base pairs. So the algorithm literally hides these sparse communication channels in the empty topological gaps between the dense data.
The squirrel chic, it's just stashing the nuts in the empty physical space.
Exactly that. And think about why this is so vital for multiomics research.
Multiomics being the study of how genes, proteins, metabolism all interact together.
Right. In traditional research, an analyst has to cross-reference hundreds of separate flat files to see the whole picture.
Which sounds like a nightmare.
It is.
Yeah.
By packing it this way, that expansion to 9.48 gigabytes is this highly calculated, intentional increase in knowledge depth. Having 54 layers of context in one unified file proves that multidimensional flow frames are just a fundamentally better way to represent reality.
Okay, so if we can fold biological data into 54 dimensions, what happens when we use these exact same topological tricks to compress other kinds of data, like the arbitrary data you and I interact with every day?
And that brings us to one of the most fascinating mechanical concepts in this whole ecosystem: topological syzygy folding.
Syzygy, it is such a fantastic word.
It really is, and it describes the process perfectly.
Yeah.
You see, standard compression algorithms, or traditional zip file, they're basically just looking for repeating patterns of text in a flat line.
Right, so if I write the word apple 50 times, a zip file just writes a note saying,
Yeah.
print apple 50 times.
Exactly. Syzygy operates entirely differently. It pushes the data into a multidimensional space. It dilates the area, analyzing the data as physical geometry, actively looking for repeating loops.
The math calls those Reademeister knots, right?
Yes.
So it's treating the data like a literal piece of string, trying to fold it over and tie it into knots where the patterns overlap.
That's a great way to picture it.
And when this geometry aligns, the results are staggering. The sources show a benchmark for a poly DNA sequence.
Which is just a long, repeating string of the A base.
Right. Standard 1D packing compresses a 100,000-byte sequence down to 250 bytes. But syzygy folding, it collapses that exact same sequence down to just 3 bytes.
Yeah.
That's a 333x compression ratio.
Because it stopped looking at the sequence as text. It mathematically described the geometric shape of the loop, found the knot, and just pulled it tight.
But, and I really want to push back on this, according to the documentation, this incredible tool has a pretty spectacular failure state.
It does.
When syzygy encounters what they call pure entropy, which is completely random, non-repeating data, it doesn't just fail to compress the file, it makes it worse.
Much worse.
If it hits a randomized ACGT sequence, it inflates the file by 8 times. And on standard brain imaging data files, these BIDS.json files, it creates a negative 412% inflation.
Yeah, blows up.
So why is a sophisticated compression algorithm that makes your files 8 times bigger somehow a good thing?
Well, the answer lies in the underlying philosophy of the algorithm, which Bitwise calls the faith investment.
The faith investment.
Right. The moment syzygy encounters data, it immediately dilates the multidimensional space. It builds this massive, complex mathematical scaffolding, hoping to find a topological history. It bets computational power up front, assuming there's a structural loop it can eventually collapse.
So it's paying the physical cost of the space before it even knows if that space is needed at all.
Precisely. And if it turns out the data is pure entropy, meaning it's mathematically random with no repeating organic loops, that massive scaffolding just sits there, completely empty.
Oh, I see.
You paid the overhead for 3D space, but there was no geometry to fill it, so the file size balloons. But the developers mathematically proved this failure state. They call it the hope gap.
Wait, let me think about the implications of that for a second. If the kernel hits this hope gap and inflates your file by 8x, it isn't just throwing an error code.
No, it's not.
It's mathematically proving that your data has no loops, which means it has no biological or structural ancestry.
Exactly.
The math is definitively telling you, hey, this data did not evolve organically. It was generated from scratch by an algorithm. It's literally a fingerprint of artificiality.
That is precisely the implication. It transforms a simple file compressor into a topological ancestry test for your data.
That is incredibly heavy. Okay, so geometry and history dictate how efficiently data can be packed. Let's pivot from how data is generated to how human meaning is transported.
Sure.
Specifically, applying this geometry to talking to large language models, AI.
Right. The industry is seeing this massive surge in real-time voice AI pipelines. You speak, The system transcribes it, the LLM processes it, generates text, and synthesizes that text back into audio.
But the bottleneck there is the audio formatting.
Huge bottleneck. Standard audio files like WAV or even FLAC are huge. They're desperately trying to preserve the exact physical sound wave of human voice bouncing around a room.
But the realization Bitwise had here is just elegantly simple. LLMs do not have ears.
They don't.
They don't care about audio waveform precision. They only care about the semantic meaning of what was said.
Which leads us to the creation of NUMA voice FLAC.
Okay.
It's a lossless wire format engineered specifically for AI. It abandons the flat audio wave entirely and splits voice data into 3 multidimensional tiers.
Let's walk through those. Tier 1 is just the phonemes, right?
Yeah, the core phonetic building blocks of language. And that tier takes up an incredibly tiny 54 bits per second.
Wow. And then Tier 2 layers on the prosody. The pitch, the timing, the energy.
Right. Because whispering "I'm fine" and screaming "I'm fine" mean 2 totally different things to an AI trying to gauge sentiment.
Obviously. And adding that vital prosody bumps the data stream up to just about 500 bits per second.
Exactly. Finally, Tier 3 is the lossless residual waveform. It uses an AI vocoder to capture the exact acoustic detail of the room, and even that lands 2 to 3 times smaller than a standard FLAC file.
It's brilliant because of the modularity. Here's where it gets really interesting. It's exactly like asking a master chef for a bread recipe.
How so?
Well, a standard WAV audio file is like the chef forcing you to download a massive uncompressed 4K video and then baking the bread.
Right, which takes forever to download.
Exactly. It hogs all your bandwidth. But NUMA Tier 1 is just the chef texting you the plain text recipe. Tier 2 adds a little margin note about how enthusiastic the chef sounded. You only ever request the massive 4K video Tier 3 if you absolutely need to see the exact microscopic crumb structure of the bread.
I love that analogy. And Bitwise handles that initial recipe layer brilliantly. Because Tier 1 is just foams, they can compress it natively inside standard web browsers using standard gzip software.
Oh, wow.
Yeah, bringing the phone data down to 2.44 bits per character. That makes it competitive with the absolute best plain text compression tools out there.
And it runs everywhere. Web browsers, node servers, Cloudflare edge networks. You don't need to install heavy proprietary software to make it work.
Right. And when you zoom out, this creates what the sources define as voice as a transport for arbitrary text. By separating the linguistic meaning from the acoustic wave, you send roughly 4,700 times less data to the AI's speech-to-text layer.
Let that number sink in for a second. 4,700 times less data pushing through the network.
It's staggering.
If you're a company running thousands of real-time voice agents, stripping away the acoustic noise radically alters your bandwidth, your processing speed, and ultimately your costs.
It really forces a complete rethink of the infrastructure.
Which naturally leads to my next question. If we are completely bypassing normal file formats and stripping data down to raw, multidimensional geometry, traditional firewalls aren't going to know what to do with it.
Not at all.
You can't put a standard digital padlock on a 54-dimensional shape streaming over a WebSocket. So how do we secure this?
That structural challenge birthed the next piece of the ecosystem, not chain. It's an edge-native blockchain.
Not chain, and that's spelled with a K, right? Not a blockchain, a not chain.
Correct. So traditional blockchains require massive farms of GPUs burning through electricity, just guessing random numbers to win a cryptographic lottery.
Proof of work.
Right. Not chain abandons that.
Yeah.
It runs entirely on Cloudflare workers, which means it costs practically nothing to operate. We're talking $0 to $7 a month.
That's nothing.
And instead of guessing numbers, it secures the network using proof of not, which verifies the topological integrity of the data stream itself.
And the speed difference is insane. The sources show a benchmark where not chain streamed secure high-definition video you can encrypt at H.264 video.
Yeah.
It streamed that data at 101.6 megabytes per second. That is 191 times faster than standard real-time video playback.
On a blockchain.
On a blockchain. It's wild.
And it achieves that unprecedented speed because of its encryption mechanism, the lacy cipher. It operates using zero-overhead steganography.
Steganography being the practice of hiding a secret message in plain sight rather than, scrambling it into obvious noise.
Exactly. Most encryption scrambles a file into random noise, which just screams to a hacker, hey, valuable data hidden here.
Right.
The lacy cipher makes the ciphertext look exactly like a valid, boring data stream. The network headers are correct, payload sizes match, but the multidimensional channels and values are mathematically scrambled. It adds absolute 0 bytes of overhead to the file.
Now, The README claims this cipher is definitively unbreakable, and I have to push back here.
Fair enough.
We have all seen every cybersecurity startup claim their algorithm is unbreakable right up until it gets hacked. What actually makes the Lacey cipher different from, say, standard AES encryption?
Yeah, it's a vital question. But Bitwise isn't just making a marketing claim here. They backed it up with formal mathematics. They built the cipher using Lean 4.
Lean 4.
It's a theorem prover language,
Okay.
basically hyper-strict math software used to verify logic so rigorously that there is zero room for human error.
Okay.
Using Lean 4, they provided a literal thermodynamic impossibility proof for cracking the cipher.
Thermodynamic, meaning they didn't just prove it mathematically, they proved it using the physics of heat and energy.
Yes, we have to look at the key space. The combined key space for the rotating Lacey cipher is 2 to the power of 2347.
I cannot even conceptualize a number that large. Ground that for me.
Okay, think about the absolute physical limits of our reality. If you took the entire mass and energy of the observable universe and converted all of it into pure computation,
Okay.
operating at the theoretical limits of physics, you'd yield roughly 10 to the power of 90 operations.
So all the energy in existence only gets us to 10 to the 90.
Right. But the key space of the Lacey cipher is so vastly larger than that. The gap to brute force break this encryption exceeds the universe's total computational capacity by over 10 to the power of 600 universes.
Wait. So if the key space is larger than the total available energy in the universe, a brute force hack isn't even a math problem anymore. It's a physical impossibility.
Exactly. A supercomputer would literally melt into slag before it got even a fraction of a percent through the combinations.
Yeah.
It is structurally unbreakable based on the fundamental laws of physics.
Okay, that is astounding. We've covered 54-dimensional DNA, voice algorithms using 4,700 times less data, and encryption that defeats the physical universe.
It's a lot to take in.
It is. To tie all this theoretical math together, how does this dimensionally aware infrastructure actually perform in the real world, like against the tech giants right now?
Well, the sources provide a direct benchmark for that. They tested sovereign mesh inference, specifically pitting the Gnosis distributed inference mesh, which uses Bitwise's special knot model, weights against Llama.
And Llama is currently one of the most popular tools for running AI models locally.
Right. The rules were straightforward. Run a comparable 1 billion parameter AI model and measure the time to first token, or TTFT.
Basically, when you hit enter, how many milliseconds does it take for the AI to start generating its answer?
Exactly. For Llama, using traditional architecture, the TTFT was 17,362 milliseconds, over 17 seconds of waiting.
Which, if you're staring at a blinking cursor, feels like an absolute eternity.
It really does. But for Gnosis, utilizing the Bitwise architecture, the time to first token was just 3,141 milliseconds. It was 5.5 times faster.
Wow.
And the reason for that speed up lies entirely in the data's shape.
Let's expand on the hardware bottleneck there, because I think this is the crucial takeaway. Traditional computing architecture is essentially like trying to drink a remarkably thick milkshake through a tiny cocktail straw.
I love that.
Right. That tiny straw is your local hard drive's read speed. When systems like a Llama try to load an AI, they have to suck this massive monolithic file through that tiny straw into the processor.
But Gnosis changes the geometry.
Yes.
When Gnosis uses the knot format, the model streamed directly from an R2 cloud bucket over the internet using specific range requests.
Okay, so it's not pulling the whole file.
Exactly.
Hmm.
The system only asks for the exact byte ranges of the neural network layer it needs for the current calculation. It flows directly into the computer's memory, completely bypassing the local hard drive.
It's the equivalent of just taking the lid off the cup and drinking the milkshake directly. Because you aren't constrained by the 1D file structure, you bypass the hardware bottlenecks entirely.
Yeah.
This means massive 70 billion parameter AI models, the kind that currently require dedicated server farms, could theoretically run completely smoothly on your standard everyday laptop.
It really proves that the hardware limitations we've accepted as concrete facts are, in many ways, just an illusion created by bad data formatting.
We have covered some truly incredible ground today. The Bitwise documentation shows us that data is not just a flat line. It has topological shape, it has depth, and it has an inherent structural history.
It's geometry.
Yeah. By leveraging this 3D geometry, we can compress repeating DNA loops 333 times over. We can strip the human voice down to a 54 bits per second whisper to feed directly into an AI.
We can encrypt streams so seamlessly that the universe lacks the energy to crack them.
And we can run complex AI models 5.5 times faster by simply popping the lid off the hardware bottleneck.
It forces developers to completely reframe how digital infrastructure should be built from the ground up.
It really does. But I want to leave you with one final thing to mull over on your own time. Think back to earlier in our discussion when we broke down the hope gap.
Right, the topological ancestry test.
Yeah, that mathematical phenomenon proving that files without a topological history are pure generated entropy. They didn't evolve organically, they were artificial.
It's a fascinating concept.
As generative AI continues to flood our internet, our social feeds, and our inboxes with synthetic text, perfectly cloned audio, and hyper-realistic video, could topological tools like this become our only reliable method for mathematically proving what is a natural creation and what is artificial? When you reach a point where you can no longer trust your eyes or your ears to tell you what's real, maybe you'll have to trust the geometry of the data itself.